Good afternoon, ladies and gents. My name is Ben Burton, VP for Energy and Sustainability at JP Morgan. Anywhere through here, want to ask questions, just throw your hands up. So basically, we're going to go through how to improve your data center. Say you've got an old data center, and there's not many things you can do these days with them without spending a lot of money. Some of the easy wins that are hanging around in just about everyone's data center is the crack unit controls, the delivery temperatures, DC airflow, fan demand, technology, chilled water demand. And then the next stage up is flow and temperature control and pumping demand, chiller staging and set point control. Which one's the laser? The red one? So basically where you're using all your energy is around the crack units and the cooling. And the key thing here is that a lot of air conditioners, they seem to run unhindered. They just run out of control, too much, too less. As you start moving on down through the systems, a lot of air conditioners sold these days is still return air control. Return air control is essentially human air conditioning. It doesn't look at what comes out the end of the air conditioner, it's always worried what's coming back. So the servers, IT, infrastructure is process cooling. Air goes in, air goes out. The server doesn't complain if it gets 10 degrees or 26 degrees. So the air delivering in majority of our data centers now is at 21 degrees C. We're looking to bring that up to around 25. I believe most server manufacturers, they get to about 26, 27, and the fans start ramping up in the machine. So you start to, it makes your PUE look better, but you're just burning more power for no reason. So it's a very fine balance between how much air, too much air, too low a temperature, or too high a temperature. So the savings are achieved with higher temperature supply. The greater the crack unit supply temperature, the higher the return temperature, the more efficient the crack unit becomes. So for every degree you go up in set point on the supply air, your cooling valve will then shut down, giving or take whatever the load is in the machine. So up here, some tests we've done on one of our data centers where we converted the machines to supply air control. So up there at 16 degrees, return air at 22, 6.3 delta, that's between the air in and air out of the quad. Supply air temperature at 16, cooling water valve 75%, fans at 70%. So you go up a degree, let it run for a few hours, it'll stabilise out. Deltas are still the same, but you see they're 50% cooling valve. So you've had a quite substantial cutback there, just for 1 degree of supply air temperature. If you've got 2-port valve control on your crack units, and you've got 50 of these units doing this, just backing off that percentage, the pump then feeding all this begins to back down. So by the time we get up to 21 degrees, I'm at 22% valve open. So on this particular data center, we had 10 air conditioners running. They were collectively, if you added up all the percentages, it was about 890%. After I put all the machines to supply air control, the average temperature was 18 degrees between these crack units, and then once we put them all up to 21, we basically went down to 350% valve open across 10 machines. So it pays to run at a higher temperature. At the end of the day, the server isn't going to thank you for running at a cooler temperature. At the end of the day, you can run it as hot as you want, but it all depends on where your UPS power starts to ramp up and you start seeing higher server inlet temperatures. But the interesting thing about there is that it's still at the same delta across the machine. So when we start, so at 12 degrees, supply water into the crack unit, and the crack units were set at 20 degrees return temperature. This is the average. This is 70% just here. This is the average of all the machines. This is I think it's about 20 air conditioners in this particular data center. And this wobbling here is the temperature delivery to the crack units varying because the chiller changing over or something else in the plant started up, the supply water got a bit hotter because all the crack units are running at 100%. The moment the water temperature in the crack unit increases, if your machine is running at 100% instantly, your data center begins to warm up. So as we went along, 12 degrees supply water, and then the crack unit temperature, supply temperature is at 16. So we come across here, so still got 12 degrees supply water to the crack unit, but then I've put the temperature up to 21 supply out of the machine. And we've just gone from 70 down to about 30%. And then along here we're still running 12 degrees. And then I put the supply water up with the crack units from 12 up to 15 degrees. And I think we jumped about 15% across all the crack units on average. And notice how that line there is nice and flat and straight. I was saying about here that the temperature of the water could vary now a good few degrees, but that will still stay the same. Well, it will go up a bit, but the temperature out of the crack unit will always remain the same. So after working out this supply air looks like the way forward, because we were seeing a lot of air conditioners that were in a circle, all working together apparently in return air control. And we've got variable speed fan drives in these machines. So what would happen is that the one machine would be close to a hot server, and the sensor in this machine would then detect, well, I'm running really high here, I've got to ramp right up. So all of a sudden you get an air conditioner doing 100% load, full fan speed, full valve opening, supplying it 15 or 14 degree supply. And that's when I went around and I added up all these valve averages, and that's where I got 680% out of 10 machines. So then I thought, well, how are we going to fix this? And the idea I had was just to move the supply air sensor down into the return air sensor into the supply air path. This is the cheap, dirty way of doing it. If you don't want to pay for reprogramming or anything like that, just move your return sensor into the supply stream and set whatever temperature you want to run it at. Instantly the machine will back off and just, regardless of what comes back, it will always throw out 21. So then I sat down and got hold of the Johnson's programming software, and I thought, well, let's have a go at trying to reprogram this. I went to Johnson Controls and they went, oh, it's going to be, they just pull a number out the air and go, here you go. And I just nearly fell off my seat when they told me how much they wanted to charge. So I spent 2 months learning how to use this damn software. And it was archaic as anything, but eventually I got my head around it. And then I ended up with this strategy here. So you've got return air and supply air, you've got 2 PID controls. Usually just this side here is all that happens inside a normal unit. So you've got the fan set point, minimum set point, fan ramp, and then the output to the fan and the output to the cooling valve. What I've done is I've basically made up an algorithm that combines both supply and return, combined it in this secret source algorithm I made up, and then basically worked out which one was more priority, and then that would control the valve. So now that we set this here to 21 degrees supply, return air sensor is then set, return air set point, mind you, is then set a degree above whatever that crack unit is doing. So if it's got 28, that one's got 30, this one's got 22, I just set it for 1 degree above its actual running temperature, because the data center is pretty static in the way the temperatures return back to crack units. The moment that the return air begins to elevate, this is where the system kicks in, and it will then override the 21 degree set point and start driving the 21 degrees, 20, 19, 18. Now, the idea with that is that you can now run your data center at whatever supply temperature you want, but the moment I turn the crack unit off in the middle, the 2 machines around it will instantly see a degree increase of air temperature. And then the two machines beside the one that's off, failed, or caught fire, or done whatever, it will then ramp up both machines around it and then supply. And if the valve gets to 100% cooling and you still haven't satisfied that return air temperature set point on the 2 side-by-side machines, then the fan will begin to ramp up. By having this system, what it's done is it's basically leveled out all the machines running, the N+25 resiliency we've got. Now I can leverage it. I can leverage all the machines, I can make them all run on an even keel. But the moment something goes wrong, either be a supply water temperature, it'd be a return, or someone goes around and starts shutting vents or blocks something, the system will then detect it and then start to ramp up. So in essence, it's a way of controlling all your machines without interconnection between the machines. They don't talk to each other, they just work purely on return air temperature. So we looked at putting supply air, pressure sensors under the floor. A lot of people go, yeah, you're going to put sensors, pressure sensors, control your fans and that. I'm like, yeah, but what happens if you put one next to a floor tile and someone moves the floor tile? You actually you lose the pressure there, and you'll find about 6 machines in the corner just ramp right up, trying to supply, maintain the pressure under the floor. If you're undersupplying a server, it'll begin to recirculate itself, then the return temperature will increase. So at the end of the day, this system just looks at the actual temperatures coming back to make a decision on where you want to ramp the fan up. So I made this in about 2009, and I went out to the States every year, an energy seminar out there every year, and I presented this, and the boss grabbed me, took me around to the paint department next door and said, "Yep, you're going to paint this thing." And yeah, so I sold it to the bank, and we've now got four data centers now running this solution. But what it enables you to do is, the more resiliency you have in your air conditioning, this system will allow you to actually leverage this and run it at the minimum amount, but maintain the minimum amount to keep your process going. So this is some of the data I've got from this trial plant. This is the data hall load. So about 650 kilowatts. It's only about half loaded at the time when we've done this. So this red line here is the chiller beforehand. The next blue, the next orange there line there, that is the chiller demand after. Also, and by doing this as well, all the crackings were running out of control. This leveled them all off at 70% fan output. So we gained about 34 kilowatts there of saving just on the fans alone. The difference in the chiller was about 89 kilowatts there. Yeah. And that was essentially a 350 kilowatt load on the chillers. So if you look about issues, probably 375, really 400 in summer, but you're looking at almost a quarter cut back on your chiller demand. Mind you, these chillers we have a CFP of about 3.8, so these old Quay machines, but we're going to look to replace them with something that's CFP of 6, a lot more efficient. So this purple line here is the free cooling. So we've got dry radiators outside that will then start up when the air temperature was below 8 degrees. But since I put the temperature, supply temperature up to 21, I don't need to run 10-degree water anymore. Put the water up to 13 degrees. And that increased my free cooling time by about 3 months. When you look at the averages of it. So if you put your supply temperature up 2 degrees, you can still put the chiller set point up 2 degrees, and you've still got the same margin of energy extraction out of the heat in the air, because you've just shifted the operating bands on the chiller and the cracking up together. You haven't lost any resiliency, you haven't lost any cooling power. Everything's just been pushed up the chart a bit. When you do that, chillers start behaving more efficiently. For every degree on your chiller, it's about 4% saving. So back to the return air supply air. So basically, you just get the sensor at the top, stick it in the bottom, set it at 21, and off you go. Just as a trial to see how much your air conditioning will back off. This is a bit of a wrong picture, it's got a DX in it. Our unit, so you can't do this on DX, you've got to do it on chilled water. So, next one. So the next thing we come up with is, well, let's get rid of these belt-driven, 3 belt-driven motors in there with 4 kilowatt motor each. Had twin V-belt drives on each one, so I had 6 drives, 6 V-belts running. You stand there with a thermal camera and I could see these V-belts just glowing, just losing heat, losing energy, just from friction. So we come up with a solution, put in EC fans, and the secret to this is the bigger the better. The bigger the fan, the better efficiency you get out, and the lower the output you got right out to do it. So what we've done, we'll see these old units here, the old scroll fans, they just blow the air straight down and it has to go that way. So that's a 90-degree turn the air has to do. The moment you do that, you lose your throw distance, you lose your laminar flow. You could stand in front of the machine, you could feel 3 blades of air just coming out at you. What we've done is we buried the fans into the bottom of the supply air plant. So that grey bit along the side there is actually the floor plate of the air conditioner. We just sunk them straight in. So I think there's a photo coming up, looking back into the crack here. But the idea is that these plug fans, they basically throw air at 360 off them. When they sit inside the supply plant there, they basically the air gets corralled, and then all of a sudden you've got a great big rectangular laminar throw of air straight out the machine. You could put like a turning blade at the back if you want to, but the amount of air that's coming through these things is just phenomenal. And inside that box section, it will actually start to push the air out in a straight square throw. So these are the old fans we took out there. Whopping great big thing. It used to run at about 60.6 power factor, which is pretty bad. Once we put these in, we can run about 0.98. So the kVA just dropped considerably. So that's looking inside the data center, looking back into the air conditioner, and this is it spinning. So we've put chicken wire up there now because you've basically got a big set of blending blades in there. You don't want no one sticking their arm in there because it'll be there. But the way the air comes out of there now is a lot more laminar. There's a lot of consideration when you put these fans in. They can't sit too close together. You get a propeller effect of the air being bashed against each other. Bit of trial and error, getting the right plates, getting the right, and you've got to make sure the plates are thick and heavy and strong so it doesn't get a resonance and get a vibration in them as well. So we put some in and we trialled it for a couple of weeks and it was making this brrr, it was like a vibration through the air conditioner and you could hear it. And the consultant who installs these fans for us, we went back and had a look at it and you could actually see the base plate drumming away. So we doubled the size of the steel work there at one point. So the bigger the fan, the better. So basically we had all the air conditioners running. I went around and along the entire floor, measured all the airflow. We had 69 cubic litres a second of air out of all the machines, out of the data center floor. That was all the fans at 100%, the V-belt drive ones. We put the new EC in, now we're getting 93 cubic litres a second at 100%. You could stand in the data hall down the back end. I held the bolometer in the air and I can get 500 litres of air a second just going through the main corridor just by holding the bolometer up. And you could stand there and your jacket would start to flap. That's just in the vacuum going back through these machines. So the savings, we've increased the data center flow rate by 21,000 litres a second of air. So commissioning the fans at 65% at the end of it. So we were running almost half. So the savings of 140 kilowatts, moving the same amount of air in the data center. And that's a base load. So when you're computing that out at about 12 pence per kilowatt hour, it's £147,000 a year. The job cost £210,000 to do it. Payback under 2 years. So when you start looking at the EC fans up here, the lower you run them, the better. So cube law with fans, with moving air and pumping water. If you slow something down by 10%, you save 25%. So we're running at 60% there, so we're running about 2 kilowatts per machine. I couldn't find the other bit of data I had for the original running, but we were running at about nearly 4 kilowatts to move the same amount of air out of that same machine. The efficiency where this comes in is where the air isn't being turned anymore, it's being thrown directly straight out. The air just travels sideways out of the machine, straight to where it needs to do its work. So all these different numbers here is where all the different air conditioners were at different stages on their return air control philosophy at the time. So some were running at 40%, some were running at 80%, so that's why you've got these really great big percentages of savings here. Most DC fan suppliers will tell you 25, some say 20, some say 30% savings, but when you oversize the fan and you oversize the EC electric motor, EC electrically commutated motor, there's no brushes, there's no metal, there's no induction, there's no bad power factor losses inside these motors. But once I leveled the machines off at 65%, I basically got a saving upwards of about 55, almost 60% to move the same amount of air, which is quite considerable when you look at base load and these things just running and humming 24/7. So this is the data center we've done this on. We used to run a 1/3 off, so we had a rotating duty cycle all the way around. And what was happening is we get a hot spot here 1 week and there'd be a hot spot there, and the phone would be going off saying, oh, what's wrong with this? This is overheating, the data center's overheating. What it was just a rotating hot spot all the way around. So crack units with the return air control of these fans will suffer a condition which I've called load hopping. The moment you could turn an air conditioner off on return air control and you turn it back on, the other one's ramped up next to it. The one you turn it on and off was running at 100% for a week. This one will now run at 100% for a week because its air movement has increased. It's pulled the heat away from that one there. So the other one here will read 24 degrees, so 23.9, set point at 24. The actual air conditioner will shut its valve. So 23.9 degree air will go into the crack unit, and then out the bottom of the crack unit will become 27 degrees. I could walk up the data center with a thermal camera, and I could basically see 15 degrees on the floor, and then I walk up a bit further, I see 26 degrees on the floor. There's a big red spot, big green spot, big red spot all the way along. And by machines running at 100%, one machine at 100%, or 3 machines running at 33% is less energy and less water movement. So, can anyone tell me what's wrong with this picture? Absolutely freezing there. It's down there, hardly anything. You're under about, well, I'm guessing probably about 20, 22 or something degrees. There's a cabinet here, there's a cabinet there, there's also another cabinet just here outside the picture. But in here you can see that the airflow all seems to be coming up through the middle. This was to do with all the floor tiles being open. You never run your data center with all your floor tiles open. If you walk through your data center floor through the cold aisle, and if anywhere along there you feel more air coming out of any one position more than the rest of it, you've got an unstable static pressure on the floor. What you need to do is go along in your data center with a screwdriver. Any floor tile that's absolutely blasting air, shut it back. Now the way I do this is a really quick and easy way of doing it. You just put your hands against the cabinet, you lean over the cabinet. If your tie's going on like that, flapping in the air around you, don't give away too much. If you can just feel a gentle breeze on your face and your servers are deployed here, that's perfect. So you just twist it back a bit, you don't need a barometer, you don't need any special equipment. And you just basically go around, walk all your aisles, shut down the ones that are absolutely flogging the air out. And then you go again, and you go back again, and then you'll find other tiles that you push it too much air, you shut them down again. So you end up with a condition where everything in your data center should be about 75%, maybe around there. But then knowing that you've got that extra capacity, what will happen is the pressure under the floor will begin to levelize out. Instead of having 4, 5, 10, 15 PA of pressure there, and you've got about 1 here, you'll find that you'll probably end up with about 8 or 9 PA across the entire floor area of your data center. So the moment you land a new piece of kit in, you can go up and go open it up a bit more, and you know you've got the air there. When you have venturis under your floor where you've got high pressure air shooting out of the crack unit, and you've got a suction point, you actually get up measured a couple of 100 litres of air a second being sucked back down into the floor because the data center wasn't held at a global static pressure because of the easy openings the air could just shoot out of. Once you get a static pressure across your floor that's even, that venturi point will actually disappear on you. So after I'd gone around and shut down all the tiles, we basically, that purple strip went all the way through and even air coming up. But the next thing is it's too cold. That's the next issue we had. So we basically went through, and this is after we'd leveled it all out, all the floor tiles. So they're all like semi-closed, so to speak. But now you can see I've got the constant temperature all the way down until I get to about here. And this is where the evil of the return air control comes into it. That point there was a blade server right next to the crack unit, just absolutely flogging out hot air. And it was hitting the sensor and it was just making the unit go 100%. This is why you get to a very dangerous condition where you start to have air conditioners at all at 24 degrees return air set point, and all of a sudden, yeah, let's do an efficiency thing, let's put them all up to 27. This load hopping and this overcooling, undercooling will become even worse because the air conditioner's got more ability to bring the air temperature down from 27 down to whatever coming out the bottom than it has from 24. So you might find you might have one doing all the work and then you might have two next to it doing nothing. So after we'd done the fan change and the control change, we had a CFD done on the data center. And this zone here had no air whatsoever before we did anything with the data center. Now, when the duty rotation was happening, a third was off, a third was off, and a third was off all the way around. Regardless, this always cooked, and there was nothing in any of these rows of cabinets, absolutely nothing. Because we couldn't put anything in there. We had servers in there, and they were recirculating, cooling themselves. So this is where we were at the starting point before the blowers were duty cycling. So the cooling potential in there was, cooling load was 23 kilowatts. The airflow was a measly, required was 2.5 meters a second. We weren't even getting 1.7. So after we put the control change, put the bigger fans in, leveled all the set points off, got rid of the zone control on all the crack units, so we just run them continuously now. I've now got a cooling potential in that zone of 60 kilowatts. The airflow, what was being used was 2.5, but now the potential of 3.4, 3.34. So by doing this, I was able to put an extra 37 kilowatts of load in that space. or 8 racks, 5 racks at 8 kilowatts ago. So after all these things we've done and other little building things we've been playing with, last year we managed to get Carbon Trust and cut our consumption back by about 12%. That was to do with some of our buildings were just running wildly out of control. Some of it was to do with probably about 5% of that was data center work we've been doing. The majority of it was just rationalising the control strategies in our buildings, just general human air conditioning. Refit a building, put LED lights, put EC fan coils in, and elevated temperature systems and cooling, comfort cooling. So we saved about $4.5 million US. It's about 2,467 cars off the road each year, and it was pretty good, right, considering that we'd only spent about on the data centers. We only spent about 1.5 million to do all this US. We did a lot of upgrades on one of the buildings, which was quite substantial. On one of them, that was another capital expenditure. So how to reduce your energy waste and make up air AHUs to data centers. This is one thing that you're at the mercy of Mother Nature outside. If it's 40 odd degrees outside, you've got to condition this air, bring it in, humidify it, and then throw it into the data center at a reasonable temperature. The amount of AHUs for fresh air makeup for DCs I've seen running at 10 degree supply is just ludicrous, because you're just throwing this air to pressurised box at high level into 30-degree environment. Why are you doing that? I can throw it in at 28 degrees, still achieve cooling, but I'm not using energy to do it. So reducing the heat and cooling delta. So the temperature where you want to heat the air and the temperature you want to cool the air, the wider that gap, the better. Reducing the dehumidification of cool coiling. If you've got a wet coil running at 6 degree chilled water, you're going to have to humidify it because you're stripping the moisture off it. Trying to blow air in the data center, it's running hot, so naturally the always want to push the humidity out of the space. Evaluate the positive pressure of the data center and reducing it. Sometimes you open the door of the data center and you just get it blown over. There's too much air. All you need to open the door is a slight breeze on you, nothing that's going to try to shut the door. I've seen some data centers where they're just running, it's like blown up like a jumpy castle. You think the wall's going to pop off the thing. So preheating coils converted to free cooling coils. So we run 13-degree chilled water. We have the preheat coil is actually running off the evaporator. Sorry, is running off the chilled water supply. Shutting down the AHUs on relative humidity sensing of the space. So if your humidity in your data center is at 50%, or it's at 60%, or it's at 45%, just turn them off, or spin them right down so you get air going in there just to keep the dust out. But just turn off humidification. Only when your humidification starts to drop. A lot of people try to run their data centers like art museums. They try to maintain 50% humidity. It's not. Circuit boards in servers these days are lacquer coated. The only time humidity was a problem was the old days, the old tape drives. You had a cellar, whatever the old tapes were made, were running past the bobbins, and that would make static electricity quite bad, destroy data on tapes. That's not a problem anymore. Everything could run between 20% and 80% now. So it's more or less in winter, you want to keep it above 28% RH in your data center. Our data center, we don't even bother dehumming it. We can go from 30% up to about 70% and back down again. It just goes like that all day. I'm not really worried about having any trouble. It's been running it like that for 4 years now. Adiabatic cooling to replace electric steam boilers and provide free cooling. So 17K delta between heating and cooling. So if the air goes below, coming out that tube, if it goes below 8, I'll start heating it with electrics. If the supply temperature coming out of there goes above 25, I'll start cooling. So probably about most times of the year, the air conditioner's not doing anything regarding heating or cooling. That's the preheat coil there. So we've got 13 degrees of water going in, we've got 8 degrees of water going out, 6.4 degrees outside. So I'm getting 6 kilowatts of free cooling just from my. So that basically negates operate that fan. So I'm achieving a 2 of these machines, I'm doing 12 kilowatts of free cooling, getting re-injected back into the cooling system, which then heads off to the crap units. So 80% dehum, 37% RH, 7% the RH added humidity. that number's quite high because these steam humidifiers have to work flat out all winter, and they're about 15.5 kilowatts each. So you've got two machines, so you're doing 30 kilowatts just about all through winter, just trying to keep the humidity above 28. When I did this screenshot, it was probably about spring and autumn or something like that, so the humidity was pretty well self-sustaining there just from the outside air temperature coming in and the humidity. So this is the adiabatic solution. So this is like a wood pulp matrix in there. You've got a little pump and you've got two sprayers in there, and that's the duty control on it. If you need 50%, one turns on, the other one turns on, you're 100. The bigger these are, they've got more pipes hanging off them. You can see down there, there's like there's 5 connections there. So I can extend that thing that way and have more stages on it. The thing is with these, you've got to run an RO plant or reverse osmosis plant, because if you just put tap water through them, that will clog up pretty quick with lime and carry on. But we have these in our building, in our fresh air machines. So these fresh air machines do 170,000 litres of air a second. What I found was we have preheated coils that run off the condenser before the cooling towers, which heats the air up to about 22 degrees, goes through one of these things, it comes out 10 degrees. I'm thinking, so hang on a minute, I'm getting cooling and humidification just out of the water. Well, hang on a minute, I'll take out the boilers, steam boilers, and I'll put in these adiabatics. I'll get cooling and I'll get humidity into the space. Just the price of pumping some water into it. The expensive part's the RO plant, but it does double the consumption. You process 20 litres of water, you've got 40 litres getting thrown to waste. So we're going to put a tank in outside that will collect that water for the toilet flushing and carrying on. So your installed data centre resiliency holds your hidden savings. Operating all your plant at a minimum, especially crack units, run them all, the chilled water, back the fans down. If you run half of your crack units or a third of them off, you're going to have to run the fans higher. Cube law, twice as fast, 4 times the amount of energy. So operating at highest temperature, remove duty rotations of your crack units if they're chilled water. Oversizing EC fans that are retrofitted to crack units. Free cooling dry coolers on the return ports and return lines from your crack units. If you run a 2-port control on a crack unit, 2-port is like water in, tap, water out. On the water outside, if you run at 22 degrees, you'll get 22, 23 degree water out. You pass that water straight through a dry cooler before it enters your chiller system. So anything below 22 degrees, you're going to get free cooling out of it. So one of our data centers, we've got the water coming back up. It goes into a main header, which is at 16 degrees, but the water coming back is at 22. And these consultants come in, yeah, we put free cooling in, blah, 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 you get this much a year. I said, where do you hook it up to? Oh, on the main return rig. That's at 16 degrees. Why don't you plug it into the return line, which is at 20 or 21? So if we start running the data center at 25 degrees supply, we're going to get 26 degree water coming back up to the crack unit. Run that through your free cooling, and as far as I'm concerned, that's free cooling almost 24/7, or at night anyway. Someone in the southeast of England anyway. So the next thing that's coming out now is high temperature chillers. So they're producing, with most chillers now, manufacturers say you can't have return water coming back to the machine between anything above 70 or 80 degrees. So what ends up happening is that the hotter the temperature of the water coming back to the chiller, it will reduce the cooling around the compressor. Once that starts to happen, the compressor works harder, you start to reduce life. Some manufacturers will just go, no, not giving you any warranty anymore. So there's a few companies, I'm not giving these guys a plug or anything, but there are companies that are producing now high temperature chillers. Some of them will actually give you 30 degrees water out and 36 back. So if you'll run your data center at 20, 26 degrees, 27, maybe even 30, you only have to supply water at 28. So in the middle of winter, the chiller's acting like a heater, if you like, because it's so cold. You get free cooling all year round. And the secret here is to run your crack units at almost 100%. So you run your crack units at 90% valve opening. You make a bit of logic that looks at all the crack units on average. If that average goes above 90, 95, you then automatically send a signal to the chiller to set a set point from, say, 18, 19 degrees, put it down 1 degree at a time until the valves start to come back. When the load on the data center begins to back off, that valve opening will begin to close down on all the crack units, and then it goes, oh, okay, I'm 10% below, I'm now at 80% valve or 70% valve opening. That will trigger some logic in your BMS to put the set point back up. Once you put the set point back up, the chiller backs off. Every degree you back your chiller off up a degree, you save about 4%, depending on the chiller. So when you're looking at, it's a 30-degree day outside, and I have to supply water at 20 degrees, and we're doing 10K of cooling. So where the chiller load comes in is where the outside air temperature versus the output temperature of the chilled water. The bigger the temperature outside and the water temperature is constant, the harder the compressor's got to work. But if you put the temperature up on the data center, on the supply water, that means the chiller will actually has less work to do. Because at the end of the day, in every chiller, in the bottom down there in the shell and tube, the refrigerant is always held at 0 degrees or 1 degree refrigerant temperature. So if you're running at 10 degrees, you've got 10 degrees difference between the refrigerant temperature and the water output temperature. If you're running at 20 degree output temperature, you've now got 20 degrees of difference between the refrigerant temperature and the output target temperature set point. So in essence, the heat exchange in the shell and tube evaporator is just goes through the roof. So then the chiller actually has to work less, with less refrigerant movement and less compressor power because it's running at a greater delta. And there's a picture of the REC fan. So all these things I do, people start, I can hear people's knees clacking together from the States and everywhere. We want to do what today? So you want to put the temperature up. So only about a year or so ago, we had a new system put in. It was like a electronic permit system. Before, we just emails were flying between each other, between stakeholders. Well, so any sort of change where I'm going to go in there and start cranking the temperature up, everybody goes, oh, you shouldn't do that. What's the risk? And all this, the back out time, if the chillers fail, or carry on. So over time, doing these projects, I started to get confidence with the lines of business of what I was doing. But what made it easier the second time around was this e-permit system that electronic based, all the stakeholders of the networks, the IT, the servers, the apps, the people running the applications, all had a say on this system. So an email would go out to everyone, and you could then they could assess what the risk is, and they would approve or reject, or they'd ask for more information. Which just because you come back in the morning, the old system, you have about 10 emails from the one person or 10 people, and all of a sudden you spend half your day answering all these silly questions. But with this, it actually categorised the risks and it identified the people it was going to go to, what did what, who did when, submit change, the days it took to go through. High risk in our company is 90-day lead time. So if I want to go do major open heart in the data centre, or we power down half the data centre, but everything's concurrently maintainable across our energy system in there, we still have 90 days for these people to have on. And it takes one person to say, oh, we're doing a major bank trade that day, work will stop, that'll be it. So in a way, it puts a lot of control on things, and most times you can talk people out of rejection. For whatever reason, they just come up with some silly idea, oh, we're doing a transfer of accounts that day, and carry on. And you're like, well, but how much is this costing you to do that? I'll tell you about £30,000 their change. I said, well, we're about to do half a million on this, but it's going to be like a big cost to back out of our shutdown at that point in time. It's also very careful how you write them as well. You've got to put the right words in there, put softly words, don't put words of turn this off, do this, put the temperature up. So assets affected, risk of works, reduction, resiliency, methodology, review, lead time, implementation. So what information goes where, who's wondering about what. At the end of the day, you can have all these things in place, but the bloke that lands in the data center to do the work, he could be an absolute cowboy. It could be a company that's been vetted, they know what they're doing, blah, 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 but someone else could turn up that day. And eventually what we ended up doing was putting names on the e-permit system, so whoever's coming into the data center, we ended up putting 10 names on there. Only one bloke would turn up, but we make sure we've got their names in, because they wouldn't be allowed in the data center otherwise. So back to the point of who's working in your data center. We've had cabling guys come in to decom cable, and I've seen them there just pulling Cat 5 out the floor, and you've got it wrapped around some little fibre noodle starting to burn into it. And I'm like, wait, what are you doing? What are you doing? You can't do that. Oh, we just pull the decom. And I said, yeah, but there's live stuff everywhere. You just can't go there to rip tearing about. It's just not on. So this is, in a way, this system combines all the RAMs and method statements and who's doing what, where, when, and how, and why. Even down to the different procedures, how they're going to do it. It's all one of those, can say chicken and egg thing, but the right people, the right time, method state, the right place, and all that. So for us, it's made our work a lot easier over the last year or so, having this new system. And as we start to roll it out across EMEA, we've already got the base print done. We just put the names of the stakeholders in that Turkish data center. We put our names into that one, or one in Milan. But sometimes there are people on every change record. There are people around the world that are interested in what's going on, and sometimes you just can't get away from that. Depending on what sort of job you're doing, there could be like 50, 60 people, maybe even 100 that have got to approve this particular piece of work. It does stop a lot of things going down and disasters and that. Thank God we haven't had any. So the other different permits we have: access permits, isolation control permits, mechanical, electrical, hot works permits, confined space permits, working at height. Those are the only ones that aren't really contained in this system. These are more localised when they're doing actually in the ground. And most times, 9 out of 10, this system here is just letting the world know what we're doing. And this one here is down to the people on the ground, making sure that they're doing the right thing. At the end of the day, it's only as good as the person you put in there and your teams that are watching these people. So the benefits of it are increased complete visibility of events, who's doing what, where, when, how, and why. Compliance, government's legislation, compliance, industry regulations, compliance with corporate governance. The benefits in reductions are injury to people, compromised security, disruption of business, damage to property, insurance premiums, legal fees and fines, management, business downtime, and reputation damage. I think everyone can vouch for that one there. You lose your data center, people will go elsewhere to do their business. We can't have that in our company. It's not even talked about. So, who will know what is in the e-permit? So suppliers, they can put the hazards in. The affected parties need to know where it's going to happen. Auditors, procurement, authorised persons. So these are where the information e-permits goes to. And it just, once you put one in, it goes out across the world. And sometimes you'll be sitting there, you'll be ringing people up a week and a half later, go, can you approve my permit, please, please? Oh, you haven't got around to it. They go, click, done. They get that many of them. Sometimes you have to chase them, but the system works. I think that's it. Is anyone got any questions on it?